Hello, welcome back. Let's solve question 6.4.1 from Arfken, Weber, and Harris. So the question states that show that the eigenvalues of a matrix are unaltered if the matrix is transformed by a similarity transformation, a transformation that need not be unitary but of the form given in equation 5.7.8. And this property is not limited to symmetric or Hermitian matrices. It holds for any matrices satisfying an eigenvalue equation of the type Ax equal to lambda x. If our matrix can be brought into diagonal form by a similarity transformation, then the two immediate consequences are that the trace, that is sum of eigenvalues, is invariant under similarity transformation. Second, the determinant, product of eigenvalue, is invariant under similarity transformation. Okay, and we'll go on to show that these are true. Okay, so first let eigenvalue equation to be this is matrix. Okay, this is matrix A, H equal to alpha H and A. This can also be written as A E H equals to alpha H. Okay, here E is identity matrix and E can be written as R into R inverse, and determinant of R is not equal to 0. Alright, so I put the value of E over here, that is A is R into R inverse H equals to alpha H. Now I multiply both sides by R inverse. Multiply both sides by R inverse from left hand side. Okay, now the equation become R inverse A R inverse H equals to alpha R inverse H. Okay, and the double dash bit under the letters represent that these are the matrices. Okay, now let R inverse H, sorry, one sec, let R inverse H represent some another vector, say H prime. Okay, now we put the value of this over here and over here. So what we get, R inverse A into R H prime equals to alpha H prime. Alright, now let's put R inverse A R equals to A prime, which implies A prime into H prime vector equals to alpha H prime. So from this equation we can conclude that eigenvalues are unaltered under similarity transformation, and same cannot be said for eigenvectors. Oh, we say this because H prime may or may not be equal to H, but the eigenvalues alpha remain same. Alright, so this is the first part we have proved. Now we'll move on to next part. So first we have to show that trace, which is equal to sum, is invariant under similarity transformation. So in this we have two things to show. So first, A is trace is invariant. This is the first thing we have to show. Second is trace is equal to sum of eigenvalues. Alright, and now second, wait a second, we'll show what's second. Second, wherein we have to prove determinant, which is a product of eigenvalues, is invariant. So what we have to show, that determinant is invariant, B determinant is product of eigenvalues. Alright, these are the four things we have to show. 1, 2, 3, 4. Okay, now we will first off head on start with trace is invariant under similarity transformation. So here we are showing 1A, that is trace is invariant under similarity transformation. So under similarity transformation, A matrix becomes A prime, that is A. Okay, now the element in the element form, the ith and jth element will be K M R inverse I M A M K R K J equals. Now we take trace on left hand and right hand side. Is equal to summation, we take a trace on this side, so it's basically I summation I K summation M R inverse I M A M K R K J delta I J. Okay, so trace is basically adding up our diagonal elements, so not much difference on that side, and we'll go on to further steps with this becomes summation I summation K summation M R inverse I M A M K R K J. Oh sorry, over here we will have now I, because we have used this delta function. Alright, now we'll change the order of summation, and it becomes K summation M summation I R K I and R inverse I M A M K. So over here we see that this is an identity operator, so this becomes summation K summation M delta M K A M K which further becomes summation k a k k, which equals to trace of a. Okay, so we can now state that trace of a prime matrix is equals to trace of a matrix. So one point A is proved. Now we'll prove one point B, that trace of matrix is equal to sum of eigenvalues. Okay, so A prime, A inverse A R. Now we already know that trace of, we have to prove that trace of A prime is nothing but sum of eigenvalues. We know that already, that trace of A prime is sum of eigenvalues. So we have these two equations with us, and now we'll head out. Trace of A prime is equal to trace of R inverse AR equals to trace of R inverse B. We have just put AR equals to B, and trace, we already know this property, the trace of AB equals to trace of BA. So we get BR inverse, and then trace of A R inverse, which is equals to trace of A into E identity vector is equals to trace of A prime, which implies, we'll put this over here, which implies trace of A is equal to summation of. So what we have got, that trace of a matrix is nothing but sum of all the eigenvalues of that matrix. And I will prove 2a. What we have to prove in 2a, that determinant is invariant. We have A prime R inverse AR. So determinant of A prime is equal to determinant of R inverse AR, which further equals to determinant of A inverse R inverse, determinant of A, determinant of R. Okay, now this equals to determinant of R inverse R. So these are like the basic properties of determinants that one must remember while they are like having their high schools. Okay, so this is nothing but determinant of E into determinant of A. This is nothing but equal to 1 equals to determinant of A, which implies determinant of A prime equals to determinant of. Now that signifies determinant is invariant. Alright, so we have proved our 2a. Now finally we prove 2b, which is that determinant is the product of eigenvalues. Okay. So we know that the determinant of A prime is equal to product of eigenvalues. Okay, and from here, from this equation, we put determinant of A prime equals to determinant of A equals to product of eigenvalues. So it's just that we have now proved that determinant of any matrix is equal to its eigenvalue if they exist. So with this we are proved 1a and 1b, we have proved 2a and 2b, and we have also proved the first statement. So with this, I guess the question has summarized a vast number of things. I hope this was helpful to you. Thank you.